So, goedenavond.
Wow.
I guess for Sam it would be goedemiddag, and maybe for some people it would be goedemorgen. Welcome to the second plenary talk of the Student Symposium in Combinatorics 2022. This is a symposium for combinatorics students and those in related disciplines, supported by Matrix, the Australian Mathematical Society, the Australian Mathematical Sciences Institute, and UNSW Sydney. It's my, those of you at the SSC, you may notice that I don't look like Thomas Lesgor. Unfortunately, we've had to do a little bit of rearranging with the chairs, but I'll do my best. It is my great pleasure to introduce Sam Mattheus, who started as doing bachelor's degree and both masters in mathematics at Universiteit Gent, right? And then he went on to do his PhD at Vrije Universiteit Brussel. I think I said that right.
It's trickier.
Working under the supervision of Philippe, Cara, and Jan de Beule, right? But I said PhD student. Actually, that's not really true because Sam defended his thesis 5 days ago. So I'm going to take this opportunity to be one of the first people who gets to call him Dr. Sam Mattheus. I'm sure a lot of us in the audience wish we were on that side of things at the moment. I'm sure you'll inspire us to get there. Right? So yeah, I see a lot of people congratulating Sam. I will do that as well. Sam's research interests are in finite geometry, algebraic and extremal graph theory, and all of the areas that sort of intersect that. And he's been had an active role in a lot of these areas for the last few years and publishing some extremely interesting results in lots of very prestigious journals. I first saw Sam give a talk at the Australasian Combinatorics Conference back in December. I think you gave that talk at 6 a.m., if I remember correctly. And it looked more awake than the Australians who are watching it at a more reasonable hour, probably. But not because your talk was bad, because it's been a long day. But anyway, and he's got a little bit of an Australian connection in the sense that Sam has worked a lot with Anurag Bishnoi, who was at the University of Western Australia, and also with Jeroen Swilwart, who is now at the University of Auckland in New Zealand. So Sam is going to talk to us about Ramsey theory, pseudorandomness, and finite geometry. So yeah, Sam, yeah. I don't know if I said that. Someone taught me that the floor is yours in Dutch and Flemish. Hiya.
You could use it, yeah.
Okay, and I'll let
Perfect,
you.
thank you. So I'll start sharing the screen. So meanwhile, I have another interesting Australian connection for you, is that both John Bamberg's son and my son have the same name. So I guess that also counts, right? Thank you. So I'm going to tell you something about Ramsey theory, also about randomness and pseudo-randomness, and how finite geometry connects into everything. So I will not only be talking about my own result, I want to give you a bit of an overview of recent results in Ramsey theory, recent breakthroughs even, and where finite geometry comes into play and where it can really help you to advance this theory. So I'll start off very basic. I'll start off with the definition of a Ramsey number. So Ramsey number is just the smallest integer n, such that every edge coloring of the complete graph Kn, so this is a notation for a complete graph on n vertices, you color all of the edges by two colors, say color 1 and color 2, and then you want to have either a monochromatic clique of order S in color 1 or a monochromatic clique of order T in color 2, right? So the smallest n, so that you're guaranteed to have this kind of structure in your graph. So, for example, if you've ever seen this definition, you've probably seen the exercise of determining R33. So let me quickly show you what it is. So first of all, I'm going to give you a coloring of the edges of K5, so 5 vertices, which is in blue as color 1, and which is the outer edges of the pentagon. And then the inner ones I'm going to color orange, which will be my second color. Right, and you can check that there's actually no monochromatic triangle, so no orange triangle or also no blue triangle. So this means that n equals 5 does not work. It has to be at least 6. And so is it 6? That's of course the question. So let's say we're looking at 6 vertices. Start from one of them, right? And then if you look to all its neighbors, there's 5 neighbors. So that means there's, by pigeonhole, there should be at least one of the 2 colors being represented more. So at least 3 times. So let's say it's blue. You should have at least 3 blue neighbors. And then if we want to try and avoid the monochromatic triangles, for sure, we should not have a blue edge here because this would create our monochromatic triangle. So let's not do that. But then we have an issue because we would have to color all of them orange in between here, and you see the orange triangle appear. So whatever you do, whatever you try, whatever coloring you do, you will always find a monochromatic triangle in either blue or orange. So that means n equals to 6 is indeed the smallest one, where you're always guaranteed to have this triangle, this monochromatic triangle appear in 2 colors, right? And so this is a very simple example. This is a nice little technique. And actually, you might think that this is an easy thing. So probably also Ramsey numbers in general are easy, but it's not, right? So determining the exact Ramsey numbers is a huge problem. And for example, R44, we don't know. R55, we also don't know. We have bounds for both, but R55 start to get a little bit further apart, the lower and the upper. And R66, we just, at the moment, with the computational methods we have, we don't ever have the hopes of even determining it exactly, right? So what we're going to do instead is we're going to look at this this number, as a function of the parameters S and T, right? So that's the idea, and we want to study it as some kind of function and get to know the behavior of this function. So the first one, before I do that, I need to introduce to you also the multicolor Ramsey numbers. It's just a straight up generalization where instead of 2 colors, you have L colors. And so you predetermine T1 up until TL, which are the monochromatic cliques that you do not wish to see. So you want to avoid them, or the other way around, you're looking for the smallest n so that you're guaranteed to have them, right? It's just from 2 to, let's say, 10 colors. There's nothing really special about it. And just one more notational introduction is that if I want to speak shortly about diagonal Ramsey numbers, so this means that all of the parameters are equal, then I will use this notation. So just RTL, and L denotes the number of times that the T appears here, right? So this is L times. So an L multicolor Ramsey number where each monochromatic triangle we want to avoid, or which we want to happen, which we want to see appear, should be equal to T, so size T. Right. So the first kind of Ramsey numbers, which we're going to study as a function of the parameters, is the diagonal Ramsey numbers. And this is where S and T are equal in the case of 2 colors, right? So this is a classical topic in extremal combinatorics, and a lot of result has gone into this topic. And for example, one of the first results were due to Erdős himself in 1947, and also due to him and Chekeris a bit earlier, which were the lower and the upper bounds on the 2-color Ramsey number, right? So you have an exponential upper bound, which is 2 to the 2t, and you have an exponential lower bound. So for sure, we know it's exponential, but what we don't know, since this is 4 to the t, and this is square root of 2 to the t, which one's the good one? Is it square root of t or is it 4? We don't know. And even though there has been improvement in these bounds, all of them have occurred in the lower order terms. So there's improvements where if you put some more terms here, you get a better bound, but actually, essentially 4 to the t is still the best we have, and square root of t is still the best we have, which is quite remarkable, I'd say. So for the upper bound, I can tell you that it's actually some sort of generalization, some neighborhood chasing argument it's called, which is just the same thing we did for R33, but well, instead of having monochromatic triangles, you have monochromatic cliques of order t. So the argument changes a little bit, but essentially this is what underlies the argument here. And for the lower bound, this bound, you have to find a graph, or rather a coloring of Kn, so that you do not find a monochromatic clique of order t. This one is what is almost the genesis of what is called a probabilistic method. So this is furnished by a random graph or random coloring, you could say. And it's a huge open problem as well to actually find an explicit graph which furnishes the exponential lower bound. We don't know any. For example, the Beule graph, if you know of this graph, is conjectured to be an explicit example, but we still haven't proved this. So even this problem is still wide open. So that's two colors. You can imagine, of course, for multiple colors, we are equally worse off. Yeah, worse, I would say. So we have this behavior. We have a direct generalization here. So if you put L equals to 2, actually other way around, you get this, and same thing here. So the lower bound is due to Lefman, which uses an idea called product colorings. It's not too terribly difficult to explain, but I won't go into the details. And the same argument as before actually furnishes the upper bounds, right? So the neighborhood chasing argument. So here we have more problems, since this one we could rewrite, for example, as 2 to the LT log L, where log is base 2. And then the problem is, well, this is an exponential lower bound in L, but this is super exponential. So what I mean is here there's L in the exponent, but here there's L log L. So this is more than linear, right? So this is super exponential and this is exponential. We still don't know which one it is, even though this is a very interesting problem and it has relations to, for example, coding theory and the Shannon capacity of graphs and all of that. But big open problem, and you see these things have been known for quite a while, so it's really a difficult problem. And also still, if you were to fix L, let's say, then the correct base of exponent is also not known if you let t grow to infinity. So here you have this 2 to the power L over 4. Here you have this, well, L to the L. So which one is it? Is it closer to the L to the L, or is it 2 to the L over 4? Again, we don't know. So there have been some improvements, as I told you, both for the diagonal Ramsey number with 2 colors, actually some very recent improvements, but substantially they haven't really moved any of these 2 bounds. But for the multicolor ones, there has been some significant improvement actually in this part. And this is what I would like to tell you about. So 1 year ago, it's been published, but the result I think is from 2 years ago, probably. Conlon and Ferber managed to improve the lower bound. And so what they observed is that you can get this upper bound. So just to compare, previously we had 2 to the TL over 4. So that's like 6 over 24. Here you go up to 7 over 24. So while it's not terribly different, it's only 1 over 24 more. It's really a breakthrough, since nobody managed to even move the 6 over 24 in, I don't know, 50 years or something. So 7 over 24, even though it's a very small improvement, you might say, it's really considered to be a great result. So this is the result I will show you, and how the ideas of randomness, but also combining them with finite geometry, are able to prove this result. So it's proved that it happens in 2 steps. So it's a very short paper. And actually the first part is deterministic. So you construct a certain graph having nice properties. In our case, we want to construct a large graph with no cliques of size t, and also few co-cliques of size t. So whatever few means, intuitively speaking, it means fewer than you'd expect, right? Whatever the precise meaning may be, you just intuitively want to have few, and we'll see why this is relevant later on. And then the next step, once you have this deterministic graph, you can use a random procedure to really show this lower bound. And this is what I will try to explain you more or less now. So the idea is as follows. So you take a graph, so you take vertices, and actually we're going to look at the edges of the complete graph on this number n of vertices. And so what we need to do in order to show this lower bound is we need to find a coloring so that there is no monochromatic cliques of any color of order t, right? So what we're going to do is we're going to take this graph G, and we're going to use it to color parts of the graph. So I'm going to color this orange, and this will be a copy of G, right? So the edges of G will be color orange in this case. And then I use another copy, and I use it to color this part, right? And maybe they overlap, but then you choose one of the 2, it doesn't matter. But what you do know is that you use these copies a few times. Let's say it's L minus 2 actually. And then let's say final color pink. Most part you do this way. But then there will be a part left, right? And actually this will be a big part still. So if you were to color this in one color, for sure you would find a monochromatic red clique. So this would be an issue. So what they do here is they use 2 colors, but they do it randomly. So they do one part uniformly at random red, and one part which they do uniformly at random black. Now, still, you're not guaranteed to have avoided monochromatic cliques because this part will not have a monochromatic clique because you chose the graph G to have no cliques of size T. This part as well, this part as well, this part as well. But here in the black or in the red one, you still might be able to find cliques. So you're not guaranteed to have avoided all monochromatic cliques. So the second step in the random process is to, and now I'm going to try and draw this clearly, is you take a random subgraph. So out of this big graph, you just focus on this piece. So you select vertices at random, you take the induced subgraph and the coloring that follows. And in this way, you can show that actually with sufficiently high probability, you will have found a subgraph which has no monochromatic cliques of order T. And the reason behind this intuitively is because there's only few co-cliques in total. And these co-cliques will actually be the cliques in this part, right? So the co-cliques in the colored parts will be the co-cliques here. Sorry, I'll do that again. The co-cliques here in the color parts are the cliques here. And so to destroy the monochromatic cliques here, you have to use two random colors and take a subgraph, and this will suffice. That's the idea of Conlon and Ferber. So this idea has been almost instantly, let's say in mathematical terms, improved. So it only took, I think, a month or something for people to improve upon this result, but this was really the cornerstone of the idea. So this idea was really the breakthrough, let's say. So for example, Yuval Wigderson managed to improve it. So instead of 7/24, we have 9/24. So we go 2 further. And the idea he had was, well, let the first step be as it is, that's fine. But the second step, I'm going to do it differently. So the second step will be using what is called random homomorphism. So what is a random homomorphism? Well, a homomorphism is just a map. Oh, this is a bit too big. A map from one graph to another graph, which has to respect adjacency. So if, let's say, x, y is an edge, and phi is the map, then also phi of x and phi of y have to be an edge, but of course in the graph G. Right. So the easiest example is if you have a graph and you have a subgraph. So if this is H and this is G, you can just use the subgraph embedding, right? So you have this abstract graph H, which you just embed into G, and obviously you will respect adjacency because of the subgraph property. So taking subgraphs can lead you to homomorphisms, but homomorphisms are much more general. Right, and this is the idea. Because of this more general context, you have more flexibility, and the extra flexibility allows you to really improve here. That's, let's say, the big picture behind the random homomorphisms. So that's roughly the idea. Of course, I want to tell you what this graph looks like, right? So how do you find a graph with these properties? Well, that's where the finite geometry comes into play. So Conlon and Ferber considered the following graph. So we're going to look at a k-dimensional vector space over a finite field. So the finite field is always denoted by fq. So q will be a prime power. And I'm going to take a non-degenerate symmetric bilinear form. So what does this mean? Well, a bilinear form, I presume you know, right? Put in two vectors and it has to be linear in the first term and it has to be linear in the second one. Non-degenerate means that, let's say you find that the bilinear form evaluated on x and y for every y equals 0, right? Then it has to be the case that x is actually the 0 vector. So this is some sort of non-degeneracy condition. It's not the most critical one, but it's so that everything behaves nicely. The symmetric condition, well, this is what you expect or what you know. This means that beta of xy should be the same of beta yx. And then that's it. This is what you need. So in some sense, you might say these are some notions that inner products over real vector spaces have. Of course, you cannot have an inner product over a finite field because you need positive definite property, right? And well, how do you define a positive number in a finite field? You can't, right? So there's no notion of an inner product. So this is more or less the translation of an inner product to a finite field. So we're going to use the same kind of language, including orthogonality, right? So using the inner product, you define orthogonality. Well, we can do the same with this bilinear form. So x and y are two orthogonal vectors if they evaluate to 0 on the bilinear form. That's the definition. Now, the main difference, let's say, is, which we will recall later on, is that we can have two vectors which are actually orthogonal, but which are the same vectors. So this is possible over a finite field. So this is something you have to take care of, and which we will also use actually to our advantage later on. So that's the main difference. And then what's the graph they consider? Well, you're going to consider this graph. This will be a recurring graph throughout. So do take note of its definition. We're going to define it as the orthogonality graph. So it's almost what you expect. So you're going to take the vectors, you might think. No, we're going to take the one-dimensional subspaces. Why are we taking the one-dimensional subspaces as our vertices? Well, if two vectors are orthogonal, x and y, then this means the bilinear form evaluates to 0 on them, but also all multiples of x will be orthogonal to all multiples of y, right? Both intuitively and both by the bilinearity, you can see this. So this means probably we should get rid of the scalars somehow, and this is done by taking the one-dimensional subspace. So this is why we consider these to be our vertices and not the individual vectors. And then adjacency is orthogonality. So it's a symmetric relation, so you do really get an undirected graph. But remember, some vectors are self-orthogonal, so you get a graph with loops, right? So it's undirected, but it has loops. Very well. So what Conlon and Ferber did, they did not take it for any bilinear form. Most of the time when we discuss bilinear forms here, we're going to consider the standard one. So the standard one being, if you take x and y, you're going to do the standard inner product over FQ. So it's just first coordinates multiplied plus second coordinates plus and so on, right? So the standard one. And then they take this bilinear form, right? And they have to take some special Q and some special K, and we'll see in just a second why. Because first of all, you need to notice that the graph consists of two parts, and this is what I call isotropic and non-isotropic points. These are just the self-orthogonal vectors, right? And these are the not self-orthogonal vectors. So you could see it in graph theory terms as the vertices having loops versus the vertices not having loops. So there's a clear distinction between the two. The number of vertices is the number of one-dimensional subspaces in your vector space. So that's just this number. And then the degree is the number of one-dimensional subspaces. One-dimensional subspaces orthogonal to. Well, let's check it out. So we're looking for all vectors so that if we put them inside of the dot, we get a 0. But this is just a linear form, right? So here is the variable, let's say big X. This is just a linear form. So this defines a codimension 1 space or a hyperplane, depending on how you want to call it. So this will actually be a k minus 1 dimensional space. So this is why the degree is this. So k minus 1, choose 1, but the q binomial instead, right? And so most importantly, you should observe that this is roughly q to the k minus 1. And this is roughly q to the k minus 2. That's the essentials of this graph. So Conlon and Ferber used this, or rather a part of this graph, to have their good graph for the first step. And it so happens to be the case when q equals 2, and when the dimension is even and equal to the t, so the t is the same t as in the Ramsey number, they're going only to take the subgraph of isotropic points, and they throw out the loops because those are not interesting to us. And you can observe that this one does not contain a co-clique on T vertices. So this is the notation for a co-clique on T vertices. It's a complement of a complete graph. So I can give you the proof in 1 minute. So let's say you have a co-clique which corresponds to vectors. Technically, it corresponds to one-dimensional subspaces, but you can just take a representative vector. So just take one vector out of every one-dimensional subspace. And now we're going to look at the beta, so the bilinear form evaluated on pairs of them. So I'm going to collect it in a matrix. You could call this the Gram matrix, but again, it's not really an inner product, but it has a similar idea. So rows and columns indexed by these vectors, and on the row and column corresponding to Vi and Vj, I'm going to put beta evaluated on Vi and Vj, right? So what is a co-clique in this case? So it is vectors that are pairwise non-orthogonal, right? So what is the product if I take two different vectors, let's say v1 and v2? Well, it's not going to be 0 because they're not orthogonal. But if it's not 0, well, there's not a whole lot of choice, right? Because you only have two elements in your finite field, so it's going to be 1. Okay, and so you can take the inner product of v1 with v3. It's also going to be 1. v4, it's also going to be 1, and so on. So actually, on the upper right corner, you're going to see ones everywhere, right? And since it's symmetric, also on the lower part, you're going to see ones. Now, what happens on the diagonal? Well, on the diagonal, you should evaluate v1 with itself. And v1 and v1, well, they're orthogonal, right? Remember, we're only taking the isotropic points. So here we will find a 0 on the diagonal. And also for v2 evaluated, v2 is orthogonal to v2, so also here we will find a 0, and so on. So you find all of these zeros on the diagonal, but everything else will be ones. Okay. Now you can see this as a matrix over the integers, or you can see this as a matrix over finite field, doesn't really matter. The eigenvalues of this matrix are -1 if we consider it over the integers, and t -1, right? So what happens over F2, so field with two elements, this becomes 1, and t -1, remember, t is even, so this is also 1. So this is non-singular, and in some sense, this means that it has full rank, of course, which also means that these t vectors that I showed you should have full rank. So these things span a t-dimensional subspace, okay? Final observation. If I am, in the case q equals to 2, and I look at all the isotropic points with the standard inner product, so remember, this means the beta is defined as follows. This way. So what does it mean for a vector to be self-orthogonal? Well, if I evaluate it for y replaced by x, I get the following. So this is just xy squared. But over a field with two elements, squaring is the same as doing nothing, right? Because 0 squared is 0 and 1 squared is 1 again. So you get actually the same elements. So the equation here becomes the following. So what you see here, this condition for being isotropic, so self-orthogonal, is actually a linear condition. This means that all the isotropic points are contained in a codimension 1 space, so in a t-1 dimensional subspace, right? So that's where all the isotropic points were. But remember, I had t isotropic points which span a t-dimensional space. So clearly this is impossible, right? You cannot span a t-dimensional space if you're contained in t-1 dimensions. So this is a contradiction. And that's why you don't have these co-cliques of size t. Second observation is that we do not have a lot of cliques of size t. So again, few is very, broadly speaking, very intuitive. I'm not going to explicitly tell you what few should be, but you can read the paper and see what it means. But here the idea, the underlying idea is the following. If I take a vertex, I just want to start building my clique one vertex at a time, right? So I'm going to pick a neighbor, and then I'm going to pick a neighbor of these two, and I'm iteratively going to construct a clique. So let's start with the first one, x. If I now look at all its neighbors, I know that it's a hyperplane. And so this will be, sorry for the interruption. Okay, so this will be a codimension 1 space, because again, remember, you have this bilinear thing. So this will be a codimension 1 space, and actually I've drawn it already. I've spoiled the surprise. X itself will be in this hyperplane, right? Because X is orthogonal to itself. So if I denote this by X perp, which is standard notation for all vectors which are orthogonal to it, this is the picture. So I take a second vector, which is orthogonal to X, so I should choose it in here, which is Y. And then I can look at the neighbors of Y. So Y for sure has to have X as a common neighbor. So it will be a codimension 1 space through X. So let's draw it like this. And they intersect in a line in my picture. Okay, so that's the second one. The third one, of course, Y is also orthogonal to itself. So it should actually be this plane. In this way, that's better. And now if you want to choose a third one, a third vector that is orthogonal to both of them, you should choose it in the intersection of x perp and y perp. So you don't have a lot of choice, you have to choose it on this line, z, right? And so what you see here in some sense is that each time you want to add a vertex to your existing clique, you have to look in an ever increasing smaller dimensional space. So first you start with codimension 1 where you get to pick, then you codimension 2 where you have to pick, and each step, the dimension of the space in which you're allowed to search for a next vertex will decrease. And by the end, you'll have nothing left to search for. So in some sense, this shows you that your options to construct cliques are very limited, and this will imply the fewness of the cliques in some sense, right? This is the rough idea why this graph has few cliques. Okay, so we have a graph with no co-cliques of size t. We have a graph which has few cliques, but of course we want the converse. We want to have no cliques and few co-cliques, so we should take the complement graph. That's more or less the idea. And so with this, you have the first step. I've showed you the idea for the second step, and that's more or less the proof. That's the breakthrough that they achieved. Now, this is not the end of the story still. So there has been another improvement by the end of last year, I believe, I think December or November. So I'll just rephrase the last one we had before, which was Yuval-Uderson's result. And I've written it slightly different. So there's not 9/24 anymore, there's 0.375, and I'll show you just why for a reason. So this was the best, and then there was this result by Will Sawen, who improved it just ever so slightly. So this is like a 2% increase or something in the result. So it's again not too terribly impressive maybe at first sight, but really it's whatever you can do exponentially improving these things, it's always big news. So again, Will Sawen managed to do so, and unfortunately for us maybe, he replaced the first step. So instead of starting with an explicit graph from linear algebra, from finite geometry, you could say, he started from a random graph. So it appears that random plus random is actually the best we have for now. So the random graph plus the idea of Yuval using the random homomorphisms for now is the best known bound on these diagonal multicolor Ramsey numbers. So you might think, okay, random is clearly always best, right? So why should we ever try and do finite geometry? Well, the story is not over, of course. There's more which we can do. So to do so, I'm going to switch scenery, and I'm going to go to the off-diagonal Ramsey numbers. So remember what I did now was take all of these parameters, T1 up to TL, to be equal, right? So now I'm going to do it differently. I'm going to do it for two colors, so RST. I'm going to fix this one. So fix it, the first one, and I'm going to let T run off to infinity, right? And then I'm going to study it for fixed S as a function of T. This is the off diagonal, because if you were to map it in a column where rows are indexed by S table, and for so columns, rows in terms of S and columns in terms of T, then the off diagonal means that if you take the diagonal where S and T are equal, and the off diagonal is far, far away from this diagonal, right? So that's what we mean by off diagonal. So we're going to fix S and T and let T run off to infinity and see what we get. And these are the best results we have so far. So for any fixed S, at least 3, of course, this S is 2, you don't want to have monochromatic edges, but this one you can never avoid. So you want S to be at least 3 for non-triviality reasons. Then we have the following lower bound and the following upper bound. So the lower bound is due to Bowman and Kivash in 2010. And this is again a random graph procedure. So this is what is called the clique-free random process, I believe. And then the upper bound has been the same one since the 80s. So this is due to Aitai, Komnesh, and Schmeredi. And what you can see is we're still far from a solution, in short. So here we have T to the power S minus 1, which is the main term. So we can forget about the log terms for just a second. And then this one is T to the power S plus 1 over 2, which is, if we forget about the log terms, still quite far off. So the only case actually where we have equality in both lower and upper bound is for S equals 3. So you can check that then here you find T square, and then here you find log T. And you can check also here it will be log T. So this is the only case actually where we know the precise behavior of this function. For all the others, it's wide open. So it's somewhere in between this and this. Again, it's a very hard problem in general to improve this, but also recently, I think this was 3 years ago by now, we had this result due to Moubai and Verstraeten, who showed not an improvement of the bound, but a blueprint for how to proceed towards an improvement of the bound, right? And they show that if density optimal KS-free pseudo-random graphs exist, I'm going to explain you what these are in just a minute, you can actually find a lower bound which has the correct exponent for t, right? So again, the log terms, I mean, you can deal with these later on. This one you should try and get first. And so if you were to find these graphs, then you have actually determined up to logarithmic terms what the behavior is of this function. So this would be amazing. Now, let me show you what these actually are. So pseudo-random graphs are essentially explicit graphs which behave in a random-like way. So how do you make it precise what random-like means? Well, in the following way. First of all, you're going to define what an MD lambda graph is. So it's a d-regular graph on n vertices, such that if you take its adjacency matrix, and of course, quickly recall that the adjacency matrix is a matrix which is indexed by vertices, both rows and columns. And you have ones if they're adjacent and zeros if they're not. This is a symmetric matrix. So over the reals, you can compute its spectrum, so its eigenvalues. Its largest eigenvalue will be this d. So this is a standard fact on eigenvalues of graphs. And then all of the other ones, you want them to be bounded in absolute value by lambda. This is what an MD lambda graph is. Now, how does this tie into the pseudo-randomness? Well, we're going to say that a graph is pseudo-random. In the literature, often they're called optimally pseudo-random, so you should always check, depending on the article you're reading, what exactly is their definition, because there's also slightly different definitions. But for us, a pseudo-random graph will be an MD lambda graph where lambda is big O of square root of d. Now, with this definition, you might object and say, well, how can you say something is big O of d if you're only talking about a single graph? And that's completely correct. When we speak about pseudo-random graphs, we actually mean a family of graphs. So you're going to construct a family of graphs, and in this family, you'll have a number of vertices, which will depend on, let's say, an I, or in our case, it will depend on Q, the size of the finite field. It will be regular for some function of Q again, and then it will have a lambda, which also will depend on this Q. And you want to have this relation between them. So taking the square root of the degree should be the order of magnitude of lambda. Because this one gives you like a rough upper bound, but it can be shown that actually also always lambda should be at least roughly square root of d. So this is Alon-Bopana theorem, if you've ever seen it, which means that if you combine them, this says that lambda should be roughly equal to square root of d. Now, this may seem like a strange condition, but actually this is a condition that suffices to show, for example, for any graph that has this property, that it shares a lot of properties with random graphs. So, for example, the random graph satisfies this property. And so if you have an explicit graph, then you can check its eigenvalues, if it's regular, of course, and you can check whether this is satisfied. And if it does, then it will share a lot of properties with a random graph of the same edge density. So you can find some properties in the book of Allen and Spencer on the probabilistic method, I think chapter 9 or 10 or something. You can really find some precise statements for graphs which satisfy this property. The main difference is it's pseudo-random, so it's really an explicit graph, right? So it's an explicit graph which behaves randomly. And then finally, we want it also to be KS-free. So this just means that it does not contain a clique on S vertices, right? So on the one hand, you have this local condition saying for any S vertices, it should not be a clique inside of my pseudo-random graph. On the other side, you want it to be pseudo-random. So globally, it should behave random-like, but locally you have this restriction. And so the tension between these two is what you're really looking for. This is where the good stuff happens. So on the one hand, you have to have this KS freeness. So this means that surely you cannot have too many edges, right? Because if you have, let's say, all edges, surely you're going to find this clique inside. So there's this bound for the number of edges. which is expressed in terms of the edge density. So the edge density is just a measure for how many edges you have, because the D is just the valency of every vertex, right? And the M is the number of vertices. So it's some measure, let's say, of how many edges you can have. And it's known that it's at most this big, right? So that's the bound. This is, I guess, due to Krivulevich and Sudakov, but I guess it was known before then. It's just like some folklore result. So this is what we would denominate by density optimal. So if you find pseudo-random KS3 graphs with edge density equal to this thing, so theta instead of big O, then these are density optimal. And so these are the kinds of graphs that Vrije Universiteit wanted to find. So if these were to exist, then you find this amazing result, this lower bound on Ramsey numbers. Now the problem is, of course, that they don't exist, right? So only for triangle-free graphs, so S equals to 3, we have them. For higher S, we have absolutely no idea where to look for them at the moment. And so even though we do have S equals 3, you can plug this in by Universiteit's work, and you get a lower bound that's actually worse than what's known by previous results. So for this case, it's not really that interesting. It's really the higher clique-free graphs, so the K4 free, the K5 free, which we're interested in. So let me just go back to the original bounds. So these were the bounds that I showed you due to Bowman and Kivas, and also AKS, so Aitai, Komesh, and Smerdi. So I have to be fair to Vrije Universiteit. The result I showed you is not the precise result they showed. They have many more in the paper, but actually they show that you can really get somewhere even if you're not density optimal. So they show that if you have a pseudo-random KS3 graph with some edge density for some alpha, you have this lower bound. So it works for any KS3 pseudo-random graph. So ideally, you can go up to 2s minus 3, but we're still far, far away from this. But what this result shows you is actually if you can do alpha equals to s plus just a tiny bit, let's say epsilon, you would be able to improve this lower bound, right? Because for s plus epsilon, you plug it in here, you get an improvement in the main term here. So this would be truly incredible if you could do it. But as you might guess, the way I phrase things, we're again not really too, well, we don't have any graphs that satisfy this. Because the best we had up until recently, again, so I promise you a lot of recent results. Again, these are the recent results. Up until recently, S minus 2 was the best we had, right? So it's just not close enough to S plus epsilon, but we're getting there. So there has been an improvement in 2019, and this was again based on finite geometry. So this is very interesting to me at least. So it's back to the orthogonality graphs, in fact. And the original construction due to Alan and Krivulevich was actually also based on this graph. And it turns out that you can really construct a KS3 pseudo-random graph from this. So they need Q to be a power of 2, and they take K to equal S minus 1. So how do you do it? You take the non-isotropic points this time, right? So you take the subgraph on the non-isotropic points. You can show that it's pseudo-random. Roughly speaking, this is not too hard to show, and the underlying idea is that if you take any two vertices, non-adjacent, they'll have equally many common neighbors. So for any two that you will take, and why is this? Because, well, the neighbors of this one are a hyperplane, and the neighbors of this one are a hyperplane, so their common neighbors will lie in the intersection of both. And because there's equally many for any two non-adjacent ones, this will be the reason why it's pseudo-random in some sense. It's just a very simple computation. Now, I'll show you why it's KS3. And this is more or less the same idea that we saw earlier. So again, take vertices, which correspond to one-dimensional subspaces, which correspond to some vectors that we can take on there. And we're going to look at the gram matrix again. So how does it look like this time? So we're taking non-isotropic points. So this means on the diagonal, we will not have zeros anymore. So we'll have some non-zero elements here, some stars, right? So these just denote some non-zero elements. So what happens on the off diagonal? Well, we take the induced subgraph of the orthogonality graph. So any two here, since they will form our potential clique, should be orthogonal, right? So V1 and V2 are orthogonal, V1 and V3 are orthogonal, V2 and V3 are orthogonal. Any two distinct vectors that I take here in my clique, they should be orthogonal. So here I get zeros, here I get zeros. And what you see now is a diagonal matrix. So for sure this has full rank because the diagonal elements are non-zero. So this means that these vectors should form an S-dimensional subspace. But that's an issue because we only work in S-1 dimensions. So you can never span an S-dimensional subspace in an S-1 subspace, right? So this is again a contradiction, and it's the same rank argument as before. So it's KS3, it's pseudo-random, and then why is the edge density the right one? Well, recall that the degree, or maybe I'll start with the number of vertices, it's roughly q to the k minus 1. So in our case, because k equals s minus 1, it's q to the s minus 2. D is roughly q to the s minus 3, so 1 q lower, 1 power of q lower. So d over n is 1 over q, and you can see that is indeed n to the power 1 over s minus 2. Yeah, so this shows the final part of this theorem. So for this choice of q and k, you really get the pseudo-random graph. And why do they need q equals to 2 to the h? Well, that's because of the regularity condition. So they take the standard inner product, they take this q, this choice of q, and then you get a regular graph. You don't get a regular graph for any choice of q and any choice of bilinear form. But for this one, it works very well. So up until recently, this was the best. And I'll show you the idea how you can do better, right? So I'll show you the construction in 3 dimensions. So I'm going to draw a picture, and it's a picture in the plane, but for some sense, I still say it's 3 dimensions, and the reason is as follows. So if I take FQ to the third, I'm going to identify it with a different geometry. So because the 1-dimensional subspaces are my vertices, and the 2-dimensional subspaces are the planes in FQ cubed. So these are the codimension 1 spaces. They are, for example, the neighborhoods of 1-dimensional subspaces. I'm going to draw these as points. I'm going to draw these as lines. So I reduce, in some sense, my dimension. And this will be the projective geometry in 2 dimensions. So by projection, in some sense, I get this 2-dimensional picture, and it really is a projection, because what you do is you take some plane not containing the origin, and then every 1-dimensional subspace will hit this plane at exactly 1 point, and it's this point in some sense that I will draw. So there's some technicalities you have to take care of, but this is the rough picture. So let's say I take a 1-dimensional subspace in my projective plane. All right, this is X. So I'm looking at all its neighbors. So I'm going to describe the neighborhood structure. So all its neighbors are on the codimension 1 subspace X perp, and X perp is a 2D space, so a line in my picture. And will the line go through X? No, because X is non-isotropic, so it will be here, for example. Right? So I take, again, some point here, let's say Y. Y is orthogonal to X, so Y perp should contain X, but it will not contain Y. So you'll have this picture. And this one, this point of intersection, I'll call it Z, and Z is orthogonal to both X and both Y because it's contained in Y perp and X perp. So Z perp should be this line, right? And now whatever you do, if you want to try and find a fourth one, which is orthogonal to all 3 of them, that's impossible, right? Because you have this line, you have this line, and this line. There's no common intersection point. So this is it. You only have triangles. And really, once you started with X and Y, there's only one triangle that contains them, the one that has Z in it. So if you look at the neighborhood structure of this graph, what you'd see is actually the following. So you get vertex X, you took an edge, but then it's actually contained in a unique triangle. So you get this, and then you have this whole flower of triangles, more or less, in the graph, right? So the triangles are really easy to describe in some sense. So the question you could ask is, well, can I not destroy these triangles and get a K3 free graph in some sense? Well, maybe you can, right? You just need to delete, let's say, this one, this one, this one, and this one, and you'll have deleted all of the triangles, at least locally. So now you need to figure out how to do it for every vertex, right? And so you can ask yourself, is this possible? And the answer is yes, for sure it's possible. It's actually been known for a long time. So this is a theorem due to Parsons, which show that this procedure can be executed. So you can really delete about half of the vertices, which will mean that the degree will also be half. So this will be a graph on Q squared over 2, roughly. And its degree will also decrease by the same amounts, also half. It will be pseudo-random because it's a big subgraph of the large pseudo-random graph, and you have destroyed the triangle, so it will be triangle free, which is also very good. And so you see that D over N is indeed roughly of this order, let's say. Now, did Mr. Parsons state the result in this manner? No, for sure he did not. I don't think he had any relation to this problem. This was a purely geometrical curiosity and a problem that he wanted to solve. So it was a combinatorial thing, but for sure there was no applications in mind for pseudo-random graphs. And so when I saw this theorem, which was, I guess, 6 years by now, 6 years ago, I had the feeling that, well, he said this only works for Q odd. Surely this is not true. Surely it should work for all prime powers, so also the powers of 2, right? And this is, well, weird in some sense because the graphs are really different for Q odd and Q even, but the geometrical idea should remain the same, right? I mean, I've sketched the procedure. There's really no distinction between odd prime powers and even prime powers. And indeed, I managed to show together with my collaborator, Francesco Pavese, that we can do the same. Now, I want to emphasize again, I don't think I even knew what pseudo-random graphs were at that time, right? This was purely out of geometrical curiosity and because I wanted to complete the picture in some sense. But looking back, it makes perfect sense to consider it in this situation. So what other colleagues of mine did, who were more knowledgeable about pseudo-random graphs, is they noticed that you can actually try and do something similar for higher dimensions. So they managed to show that indeed you can do the same triangle deleting procedure in higher dimensions. So this KS free graph you have, you can make it KS minus 1 free as well, right? So you can delete the maximal cliques in some sense and still get a graph of roughly the same edge density. So half of the number of vertices, half of the degree, but cliques which are one size smaller destroyed. So it is really the Alon-Krivelevich graph in some sense, but only half of it. And that's why you get the improvement. So recall, Alon and Krivelevich had alpha equal to S minus 2. This one has S minus 1, right? And the reason is because from KS plus 1 free, we went to KS free in some sense. And so again, they do need Q odd. So looking back at this result, I facepalmed probably almost instantly because I had considered this problem. I just didn't know there was actually some relevance to pseudo-random graphs. So again, there was this restriction for Q odd. And so I told Francesco, I said, surely, again, this cannot be the case. So you can, in fact, do it also for the powers of 2. Now, had we only known about the problem earlier, right? Because the funny thing is we did consider the higher dimensional case, but we even told each other, I mean, like, what's the point of generalizing? Nobody will be interested in this generalization, right? Because we just didn't know. So I want to quickly sketch you the construction because, well, it's a bit more involved, let's say, than just deleting the triangles, even though the geometrical picture is not too hard. So what's the geometrical picture? So first of all, in this space, in this vector space, you look at the set of one-dimensional subspaces, which are isotropic. So these are the isotropic subspaces. So let me just quickly write here. So this is the first blob. And then I'm going to partition the whole space into copies of this blob. So this will be blob number 2, blob number 3, blob number 4, and so on, right? So the whole thing is partitioned into these blobs, which are copies of the isotropic. So you really move it around in some sense. And now if you do it well, what you notice is that the maximal cliques, they're always scattered over multiple blobs. So let's say I have a K4 here. there's never a K4 contained in one single blob. It will always spread out over multiple blobs. And so what's the idea? Well, if you can now select the right blobs, so let's say I pick this one and I pick this one, I will have destroyed essentially the K4s because I will only consider the induced subgraphs on my orange blobs. And so suddenly now from K5 free, I want to K4 free. And this is the idea that underlies both Anurag Bishnoi, Valentina Pepe, and Ferdinand Ehringer's work, and also our work. So this is the rough sketch, let's say, of why it works. And what you need to take care of is that you can actually take enough blobs. So you want to take half of the blobs, roughly speaking, and then it all works perfectly. Right. So the question is, of course, can we do better with finite geometry? So let me just tell you that for s equals to 3, these graphs were known, as I told you before, and the first construction was due to Alon. And I have to admit, this is a construction which is a deus ex machina to me. It uses the properties of BCH codes, but honestly, I don't understand it at all on an intuitive level. So it's really a mystery why this works. But luckily for us, Coparti managed to give a more geometrical construction, which also works. And here the ideas are really clear to me. So Valentina Pepe, who you saw just earlier, also managed to give a different construction for the triangle free case. And also I managed to give a different construction. But honestly speaking, they're really based on Swastik Coparti's idea. And all of them are Cayley graphs as well. So this is like a defining feature. I think the property of being Cayley graph is necessary to really prove the pseudo-randomness of everything. So because the pseudo-randomness is based on eigenvalue information, and the eigenvalues of Cayley graphs are really not too hard to compute. And this takes care of the pseudo-randomness in some sense, right? So why do I want to highlight my own construction at the very last? Not because I'm a very narcissistic person, but because it's again based on this orthogonality graph. So if you make the right choice of prime power, so not power of 2, not power of 3, you go to the right dimension, you can indeed find a pseudo-random triangle-free subgraph, which satisfies everything you need here. So it will be density optimal. And so first you have to start with the orthogonality graph. You take the induced subgraph on the isotropic points, and then you take again a subgraph. So you have to delete some edges to destroy the triangles in some sense. And if you do so, you do it in a good way, you can still keep the pseudo-randomness property, and this will be exactly what you want. So for the people who are more into finite geometry or who are interested in finite geometry, I suggest you go to Thomas's talk later this week, because this is actually what is known as a generalized quadrangle. And also Thomas will talk about these objects. So if you want to learn more finite geometry, I suggest you go and see that talk as well. All right, so the final big open question is, of course, can finite geometry help us any further? The million-dollar question is, can we push all the way up until the hypothetical, the theoretical limit? That would be very nice, of course, but probably quite difficult as well. So maybe we should settle for a little bit less money and go for the $1,000 question and see if we can really push beyond alpha equals to S, right? So there we will already be very happy as well. So I mean, you do want this alpha equals to S plus epsilon. That would be great, because you would improve the off-diagonal Ramsey numbers, and people around the world in extremal combinatorics would be very happy to see the result. So that's all I had to say. Thank you for your attention, and I hope you enjoyed the talk and you learned some finite geometry as well. Thank you very much.
Okay, let's thank Sam with some virtual applause. I'll do an audible one. Do we have any questions for Sam? I think we have time for maybe a question or two. Thomas, thanks you for the publicity for this talk. Yes, Thomas' talk is one of the very last ones of the conference on Friday evening, Sydney time. Do we know if the Vrije Universiteit theorem is essentially tight? Do we know that it is for S equals 3 but larger S?
Sorry, can you repeat the question? What do you mean by tight?
Do we know? Okay, let me.
Do you mean the logarithmic terms or?
Thomas?
I cannot see the.
You cannot see the.
Yeah, I tried to click on it, but it doesn't work for me for some reason.
Maybe I'll read the question. I'll read the question again as is written. Do we know if the Vrije-Universiteit theorem is essentially tight? We know that it is for S equals 3, but for larger S. So instead of trying to improve the density of KS-free pseudo random graphs, could the theorem be improved by having a lower bound depending also in S? So if the denominator of the lower bound, where T is a power of alpha plus S minus 2, this would be a tight results for alpha equals S.
Right. So you wouldn't need a density optimal. You could do it slightly worse, but still achieve the tight lower bound for Ramsey. That's what you mean, right?
I think that's what. Yes, he's.
Yeah. Good question. First idea I would have then, if you could do it slightly worse pseudo random graphs, then what would the best ones give you, right? Would they go over the bound? So that's like a tricky thing that would happen then. So I guess I'm not an expert in this part of the graph theory proof, but I would guess not, no.
Okay. Yeah.
Maybe the logarithmic terms, maybe, but I think for sure the main term will probably not be possible to improve.
And a kind of related question, like, do you think we could relax, so you're looking at optimal pseudo-random graph. Can you relax a bit the condition on the eigenvalue?
Yes, so I didn't, sorry, go on.
No, go on.
So I didn't mention the result, but also Wigderson together with Hay has a result on multicolor Ramsey numbers where they do relax the optimally pseudo-random. So they call it weakly optimal, I believe. And then there's this relation between D and lambda. So it's like the exponent also contains some alpha.
Yeah.
And you can do with slightly worse alphas than, let's say, 1/2, like the square root of D. And that's what their result shows. Because the nice thing is that actually Vrije Universiteit also use this random subgraph idea. So again, if you do the random homomorphism idea, you can actually do slightly better. So it's really nice that it's like this common framework where you do get the improvements.
Okay, I need to read.
It's a bit more technical to state, so that's why I left it out.
I need to read that theorem.
It's a must read.
It is an amazing one. I remember the first one I saw that. But so do you have hope in the end, like you personal?
Personally, I hope to be able to push towards the $1,000 question, let's say. I mean, together with my colleagues in finite geometry, like Valentina Pepe, Ferdinand Deringer, we're trying and discuss if we have some ideas. Valentina has some very concrete ideas she wants to try, but I mean, I have some ideas, but there's nothing really, let's say, that I'm optimistic about that will give the result. But at least there's this whole idea of this field of ideas, let's say, where we can try something finite geometrical and hope to improve.
We don't even have a construction to match the lower bound today, like to have alpha equal S.
No,
we don't know.
So even alpha equals S would be nice.
Yeah.
At least for the pseudo-random case. If you want to improve pseudo-random and do Ramsey, then you need S plus. Yeah, but
just matching the lower bound.
Just matching would be great as well. Yeah. For sure, your advisor is also interested in this problem.
Maybe.
Well, I need to know. All right. We'll just take this last question very quickly, if that's okay. So Tom was asked if you could explain again the connection to Shannon capacity, which you mentioned at the beginning of the talk.
Right. So now I need to think a little bit. So there's this series of inequalities for a graph, which involve the Shannon capacity, the independence number, the Lovász theta, and I think there's one more, but I forgot which one. And so there's this 4 quantities associated to graph, and it's been shown that actually each one cannot be bounded as a function of the previous one. So you have, let's say, alpha is at most theta, then there's results, no, alpha is at most, let's say, Lovász theta, then there's results that say you can have graphs with fixed alpha and unbounded theta. So you will never be able to hope for a function in terms of alpha that can give you an upper bound for theta as well, right? So for all of these, this connection is known except for alpha, and so the independence number and the Shannon capacity. And so showing that which which kind of behavior it is, either super exponential or exponential for the multicolor Ramsey number, will show you whether it can be done or cannot be done. I forgot how they match up, but this is like the rough idea, let's say.
All right.
I can just interrupt you for a second.
Sure.
Maybe I can point you towards the Yuval Wigderson. He has some notes on this thing, so you can read about it there, and he has really explained it well. So definitely read those if you're interested.
All right, I think we need to leave it there. Bedankt voor die fantastische presentatie. Did I say that right?
Wow, you practice so much, I can hear. Yeah, thank you.
All right, let's give Sarah a big round of applause.
Thank you very much.